Hello everyone, this is Monica Lupion and today I will review the three examples included in the presentation related to unsteady state conduction. This is part of the online course CE 318 Heat and Mass Transfer. If you remember from the presentation related to unsteady state conduction, we studied different methodologies to solve the general equation, and in particular, we focus on the analytical methods and graphical methods. In relation to analytical methods, we saw that there are two different cases, very interesting. One is when the internal resistance is very small, and the second one when the surface resistance is very small. In the first case, when the internal resistance is very small, we studied that the Biot number will be lower than 0.1. Those systems are called lumped systems, and in such cases, we can directly use this solution here, correlating the temperature and the time through the Fourier number. The second case, when the surface resistance is very small, we can consider that the temperature over the surface of a solid remains constant and is equal to T infinity. We can consider surface resistance very small when the Biot number is large. Then we review the graphical methods available to solve the general equation for unsteady state conduction. Those are the Heisler charts that you can find in the Appendix F in your textbook. Using those charts will allow us to relate the temperature and time. Let's begin with example number 1. And I would like you to stop this video for a couple of minutes, read through the problem, and make sure that you understand everything that is said. Consider a gold sphere of 15 millimeters diameter that is dropped into a water bath that is 219 Kelvin. If the thermal velocity is 2 meters per second and the initial sphere temperature is 400 Kelvin, how long will it take for the centerline temperature to reach 310 Kelvin? The convective heat transfer coefficient H is 2000 watts per square meter per Kelvin. Gold has a density of 19,300 kilograms per cubic meter and thermal capacity of 129 joules per kilogram per Kelvin. First of all, we draw a very simple diagram. This is the sphere, and this is the water bath. These are the data, the information that we have, that it is provided. The convective heat transfer coefficient, the density, thermal capacity, the diameter of the sphere, the T infinity, and the initial temperature. We need to find out the value of the thermal conductivity, and since we know that the sphere is gold, you can directly go to Appendix H when there is a table, and there are the different values of thermal conductivity for common materials, including gold. We need to calculate how long it would take for the center line of the sphere to reach 310 Kelvin. First of all, we need to ask to ourselves, is the Biot number is very small? Because if that would be the case, then we know that the resolution of the problem will be simplified quite a lot. So let's calculate the Biot number first. The Biot number is defined as the convective heat transfer coefficient times the volume of the body over the area and over the thermal conductivity. The Convective heat transfer is 2000 watt square meter Kelvin. The area is 4 over 3 pi and the radius 3. The thermal conductivity is 293 and this is the area of a sphere. We know all what we need here. So making the calculations, the period number is equal to 0.014, which is obviously lower than 0.1. That means that we can consider the system as lumped system, which is a good news, by the way, because then we know that we can directly use this equation here that correlates the temperature and time. Okay, so let's play around with this equation and taking a normal log. We have the normal log of the temperature we see, which is 310, minus the temperature infinity, which is 290, over the initial temperature, which is 400, minus the T infinity, which is 290, is equal to minus the convective heat transfer coefficient, which is 2000 watts per square meter Kelvin, times the area of the sphere, times time, over the thermal, heat capacity, 129, times the density, which is 19,300 kilograms per cubic meter, times the volume of the sphere. We have everything we need to solve the time from this equation, and doing all the calculations, time is equal to 16.6 seconds.